Whatever I had to tell you, I product out to you is delivered in this video. Now you use it, how to benefit yourself of it. And I really hope that you will get a clarity at the end of this video. And here is the problem from eigenvalues and eigenvectors, and we have to diagonalize the matrix A. For that, first of all, we have to find out the characteristic values. For that, the characteristic equation is, the characteristic equation of A is nothing but modulus of A minus lambda I is equal to 0. So I have to take lambda from all the diagonal elements. So this is 3, this is 2 minus lambda, this is minus 1, 2, 1, minus 1 minus lambda is equal to 0. First of all, I have to find out the characteristic equation. For that, this is 1 minus lambda times of, see, I have to close this row as well as this column. So if I close this row and column, see, my multiplication will be, this will be 2 minus lambda into minus 1 minus lambda, and minus of minus, this will be plus 1, and here the second term is minus 1, so I have to write plus 1 times of. So this will be, now I have to close this row and column, so this will be 3 times of, this is 3 into minus 1 minus lambda, and minus of minus, this is plus 2. And the next one is 4 here. So this is plus 4 times of. Now I'll close this row and column. This will be 3 ones are 3 minus 2 times of, this is 2 minus lambda is equal to 0. So now if I multiply, see what happens here, 1 minus lambda times of, this will be minus 2 lambda. This is plus lambda and plus lambda square plus 1 plus, this will be minus 3 lambda plus 2, and this will be 4 times of 3 minus 4 plus 2 lambda is equal to 0. Now see, this is 1 minus lambda times of, this is lambda square minus lambda minus 1, and this will be minus 3 lambda minus 1 plus 4 times of, this is 2 lambda minus 1 is equal to 0. So if I multiply with 1, this will be lambda square minus lambda minus 1, and for one time, and minus lambda times of lambda square minus lambda minus 1 plus minus 3 lambda minus 1, this is 4 times of 2 lambda minus 1 is equal to 0. So if I multiply, so this is lambda square minus lambda minus 1, so this will be lambda cube plus lambda square plus lambda, this is minus 3 lambda minus 1 plus this is 8 lambda minus 4 is equal to 0. So if you see, if you observe properly, then there is only one single lambda cube. So this is only single lambda cube we have, and the next one is, so this is 2 lambda square. So we got, so here if you see, so this is 2 lambda square here. So this is 2 lambda square, and after that if you see, so this is plus lambda square and minus lambda square. So what remains here, that is 8 minus 3, so which is nothing but 5. So this will be plus 5 lambda, and the next one are the constants. See the constants here, so this is minus 4, minus 1 and minus 1 again, so which it is minus 6. So this is minus 6 is equal to 0. So if I multiply with minus lambda cube minus 2 lambda square minus 5 lambda plus 6 is equal to 0. Now I have to find out the roots for this. So for finding the roots, see, so quotient of lambda cube is 1, this is minus 2, minus 5 and 6. Now first time I'll check with 1. So if I check with 1, see, so this is 0. So this is 1 ones are 1, so this is minus 1. So if I multiply, this is minus 1, so this will be minus 6. If I multiply, so this is minus 6 again. So this is 0, and what remains here? So here, so one root is 1, so this is lambda minus 1. And the next one here is lambda square minus lambda minus 6 is equal to 0. So this will be lambda minus 1. So what are the factors? That is 3 lambda plus 2 lambda minus 6 is equal to 0. This will be lambda minus 1 times of, if I take lambda common, this will be lambda minus 2. If I take 2 common, this will be lambda minus 3 again. Again, if I take lambda minus 3 common from this, see what happens. Lambda minus 1 times of, if I take lambda minus 3 common, this will be lambda plus 2 is equal to 0. So lambda minus 1, so this is lambda plus 2 and this is lambda minus 3 is equal to 0. So I got the lambda values as 1, minus 2 and 3. So these are the eigenvalues. So first of all, so these are the eigenvalues of A. So after finding the eigenvalues, we have to find the eigenvectors corresponding to these. So first of all, we have to find out the eigenvectors. So for that, the eigenvector corresponding to lambda is equal to 1. See, for lambda is equal to 1. So in this equation, so in this det, if we keep lambda is equal to 1, see what happens here. So this is 1 minus 1 minus 1 4 and this is 3. In place of lambda I am keeping 1. So this will be 2 minus 1 minus 1. This is 2 1 minus 1 minus 1. So this will be 1 minus 1 which is equal to 0. So this is 0. So this is nothing but 0 minus 1 4 and this is 3 1 minus 1, this is 2 1, this is minus 2 and this is minus 2. Now I am going to interchange R1 as well as R3 for my convenience. So row 3 and row 1 are interchanged. 1 2 minus 2, this is 3 1 minus 1, this is 0 minus 1 4. First of all, as you know that I am using the first diagonal element to make these 2 0. It is already 0 and I have to make this 0 using this. So for that R2. So I have to multiply with 2. So this is 2 R2 and again I have to multiply with 3 minus this is 3 R1. So this is the only operation I am going to make. So row 1 is as it is 1 2 minus 2 and row 2, so row 2 this is 2 R2, so we have to multiply with 2, that is 6 2 minus 1 minus and I have to multiply row 2 with 3. So this is again 6 3 and this is plus 6 and see what happens here. 6 minus 6, this is 0, this is minus 1, this is 5. So see here, this is minus 1 and this is minus, see here, this is minus 1. So 0 minus 1 and 5 here. If you observe this one, 2 R2, so 2 3 is a 6, 2 2 is a 2 and this is minus 2. So if it's minus 2, so this will become plus 4. So this is going to be plus 4 and this is as it is 0 minus 1 4. And the next one is the next diagonal element. I am using this. So first I use this and made these two 0 and using this I have to make this 0. So then R3 will be, that is R3 minus R2. So minus R2. So this will be 2 1 minus 2 0 minus 1 4 and if I subtract from this minus 1 plus 1 this is 0 and 4 minus 4 this is again 0. If you observe what is the rank here. So the rank is equal to 2 and the number of unknowns. So the number of unknown values, as it's a 3 by 3 matrix, x1, x2, x3. Therefore, the number of independent solutions which we can take, though the number of independent solutions is n minus r, this is 3 minus 2, one independent solution we can choose of our choice. This is 2, 1 minus 2 and this is 0 minus 1, 4 and 0, 0, 0 into this is x1, x2, x3 is equal to 0, 0, 0. So here if I multiply this will be 2x1 plus x2 minus 2x3 is equal to 0. So this is minus x2 plus 4x3 is equal to 0. So one independent solutions which I can take, I am taking x3. I am taking x3 is equal to k. So if I take x3 is equal to k, then x2 plus 4k is equal to 0 and x2 is equal to 4k. So after getting the x2 value, again if I substitute here in this equation, I will be getting x1. So 2x1 plus x2 minus 2x3 is equal to 0. This is 2x1 plus 4k minus 2k is equal to 0. That is 2x1 plus 2k is equal to 0. That is 2x1 is equal to minus 2k. If I cancel this one, so x1 value, so x1 is equal to minus k. So I got all x1, x2 and x3 values. So this is x1, x2 and x3. So What is x1 here? x1 is minus k, x2 is equal to, this is 4k and this is k. So if I take k common, so this will be minus 1 4 1 into k, which is x1, x2 and x3. So this is an eigenvector corresponding to the eigenvalue lambda is equal to 1. So remember this one. So this is minus 1 4 and 1. So if you observe this one, for 1 I got the eigenvector as minus 1, this is 4 and this is 1. For lambda is equal to, this is 1. And the next one, I have to go with lambda is equal to minus 2 now. So for that, see, for lambda is equal to minus 2, I have to put lambda is equal to minus 2 in this determinant. So the eigenvector related to, see here, this is the eigenvector related to lambda is equal to minus 2. So if I keep minus 2 here, this will be minus of minus plus 2, this is minus 1 4, this is 2 plus 2, this is minus 1 2 1 minus 1 plus 2, and this value will be, this is 3 minus 1 4, this is 3, this is 4 minus 1, this is 2 1 and 1. So this will be 2 1 and 1. So using this, as you know that first I am going to use this first diagonal element and make these two 0. Then my operation will be R2 is equal to, it is very easy, this is R2 minus R3. And the next one, R3 will be, I have to multiply with 3, that is 3 R3 minus, this is 2 R1. If you observe this one, R2 is equal to R2 minus R1. So this is R1, row 1. So if I subtract R2 from R1, I'll get 0 here. So using this, so this is R2 minus R1. So R2 will be R2 minus R1. So what is R2 here? R2 is 3 4 minus 1. This is 3 4 minus 1 minus R1. Again, that is 3 plus 1 minus 4. So first row 1 is as it is, that is 3 minus 1 4, and row 2 will be 0, this is 5 and this is minus 5. And if you observe this one, 3 R3, so row 2 will be 3 into R3, so I have to multiply with 3. 3 2s are 6, this is 3 and 3, this is minus 2 R1. So I have to multiply each and every row 1 with, see here 2. So this will be 6. So this is minus 2 and this is 8 again. So this will be 0, this is 5 and this is minus 5. If you observe, I have to use the second diagonal element to make R3 0. So for that, my operation will be R3 is equal to, it's very simple, R3 minus R2. So R3 minus R2. So 3 will be as it is 4. This is 0, 5 minus 5. If I subtract, so 5 minus 5, 0, minus 5 plus 5. This is also 0. So here if you observe, what is the rank here? The rank is equal to, again the rank is equal to 2. The number of unknowns, so the unknown values are 3, and the number of independent solutions, the number of independent solutions are n minus r. This is 3 minus 2, 1 independent solutions we can take of our choice, that is 3 minus 1 4. This is 0 5 minus 5, 0 0 0 into here it is x1 x2 x3 is equal to 0 0 0. So this is 3x1 minus x2 plus 4x3 is equal to 0. This is 5x2 minus 5x3 is equal to 0. One independent solution I can take, that is x3 is equal to k, I'll choose. And if I substitute, this is 5k is equal to 0, 5x2 is equal to 5k. If I cancel, x2 is equal to k. So x2 value is equal to k. If I substitute both the values here, that is 3x1 minus x2 plus 4x3 is equal to 0. That is x2. What is x2? This is minus k, and this value is again plus 4k is equal to 0. So 3x1 plus 3k is equal to 0, and x1 is equal to minus k. If I cancel 3 here, you take common. So all the values are ready. Therefore x1, x2, x3 values are nothing but, what is x1? This is minus k and plus k. So the value will be minus 1 1 1 into k. So this is the eigenvector corresponding to lambda is equal to, this is minus 2. So now I have to substitute. So here for lambda is equal to -2. So what is the vector here? That is -1 1 1. So this is -1 1 1 for lambda is equal to 2. And next I have to go with lambda is equal to 3. So the eigenvector now corresponding to lambda is equal to 3. Now let's go for that. So the eigenvector for corresponding to lambda is equal to 3. Now I have to substitute lambda. So now I have to substitute lambda in place of this one in this determinant. So now if I substitute, this will be 1 minus 3 minus 1 4. This is 3, this is 2 minus 3 minus 1 2 1 minus 1, and this is minus 3. So this will be, see, this value will be -2 minus 1 4. This is 3 minus 1 minus 1, and this is 2 1 minus 4. This value is 2 1 minus 4. Now I have to use this first diagonal element to make these two 0. So first, using this, I have to make this 0. So R2 will be, see here, I have to multiply with 2, that is 2 R2, and again I have to add and multiply with 3 R1. So I have to multiply with 2 and 3, and I have to add up. Then R3 is very easy. So using this, I have to make this 0. So if I add both, that is R3 plus R1. See what happens here. So R1 I am not disturbing. So this will be -2 minus 1 4 as it is. And R2, coming to R2, see here, the row operation for R2 is, this is 2 R2 plus 3 R1, 2 R2. So row 2 we have to multiply with 2. This will be 6 minus 2 minus 2. See here, 6 minus 2 minus 2. And I have to multiply with the 3 here. So this will be -6 minus 3 and plus 12. And see, this will be 6 minus 6 0. This is -5, and this is plus 10. And coming to this one, R2 plus R1. So R3. Coming to R3, so this is R3 plus R1. So what is R3 here? This is 2 1 minus 4 plus this one -2 minus 1 plus 4. So this is 0 0 0 0. If you see, if you observe this one again, the rank is equal to 2. Number of unknowns is equal to 3. Therefore the number of independent solutions is n minus r. This is 3 minus 2. This is one independent solution we can choose of our choice. So this is -2 minus 1 4. This is 0 minus 5 10, and this is 0 0 0. Into here it is x1 x2 x3 is equal to 0 0 0. If I multiply, this is 2x1 minus x2 plus 4x3 is equal to 0. This is 5x2 plus 10x3 is equal to 0. So one independent solution we can choose of our choice. Therefore x3 is equal to k. If I take x3 is equal to k, then 5x2 plus 10k is equal to 0. 5x2 is equal to 10k, and x2 is equal to 2k. And after getting the x2 value, again I have to substitute here. So the equation is 2x1 minus x2 plus 4x3 is equal to 0. This is 2x1. What is x2 here? This is 2k plus 4 times of k is equal to 0. So this is 2x1 minus 2 plus 4k is equal to 0, minus 2x1 plus 2k is equal to 0. 2x1 is equal to 2k, and x1 is equal to k. And after getting all the values here, so this is x1, x2, x3. See here, what is x1? So x1 is nothing but k. And what is x2? So this is nothing but 2k, and this value is k. So if I take, this is 1 to 1 into k, so which is x1, x2 and x3. Therefore this is the eigenvector corresponding to lambda is equal to 3. Now I am going to substitute here. So for lambda is equal to 3, what is the eigenvector? So eigenvector is nothing but 1 2 1. So this is 1 2 1. So this is nothing but, this is 1 2 and 1. So the model matrix now is ready. So all the eigenvectors, So if we write in one form, so this will be the model matrix. Therefore, the model matrix is, the model matrix P is equal to, I am showing, so for lambda is equal to 1. So I am showing this one. For lambda is equal to 1, this is minus 1, 4, 1. So this is minus 1, 4, 1. For lambda is equal to 2. See here, for lambda is equal to 2. Minus 2, the eigenvector is minus 1, 1, 1. So this is minus 1, 1, 1. And for lambda is equal to 3. Just now I have done. So for lambda is equal to 3, this is 1, 2, 1. So this is nothing but, this is 1, 2 and 1. So this is the model matrix. And after finding the model matrix, so we have to find the P inverse. So P inverse, for that, determinant of P is very important. So this is nothing but, so what is P inverse? So determinant is nothing but, I'll show you. So with this, so for minus 1, so this is minus 1 times of, so now we have to close this row as well as this column. So this will be 1 minus 2. So this is 1 minus 2. And for this one, for the middle one, this is minus 1 plus 1 times of. Now I have to close this one. So for closing this one, this will be 4 minus 2. This is 4 minus 2. And for the last one, this is plus 1 times of, this is 4 minus 1. So 4 minus 1. So mod P will be minus 1 times of, this is minus 1, 2 and this is 3. So mod P will be 1 plus 2 plus 3 and mod P is nothing but 6. So remember, I got mod P is equal to 6. And P is equal to, see here, this is minus 1, 1. This is 4, 1, 2 and this is 1, 1, 1. So we have to find out the cofactor of P. So for cofactor of P, see what happens here. This is plus, minus, plus, minus, plus, minus, and this will be plus, minus, plus. And the first, for the first position here, minus 1. So we have to close this row as well as this column. So for closing this, this will be 1 minus 2. So this is minus 1. And for the second position here, so we have to close this row as well as this column. So this will be 4 minus 2. So this is 2 here. See, for the last term, this one, this is 4 minus 1. So this value is 3. And the next one, for this value, so we have to close this row as well as this column. Then this will be 1 minus 1. For this position, we have to close this row as well as this column. Then this will be minus 1 minus 1. So this is minus 2 and this will be plus 2. For the middle one, so for the middle one, if we close this row as well as this column, see, this is minus 1 and again minus 1. So this will be minus 2. And for the last one, so if you close this row as well as this column, this is minus 1 plus 1. So this is 0. And for this one, if you close this row and column, this is minus 2 minus 2. This is minus 3. So this position. So for the middle position, so if I close this row as well as this column, then this is minus 2 minus 4. This is minus 6. So this will become plus 6. And if I opt this one, if I close this row as well as this column, this is minus 1 plus 4. So this is 3. And after getting the cofactor matrix, so we have to find the adjoint of P. So adjoint of P is nothing but the transpose of this. This is minus 1, 2, minus 3. This is minus 2, minus 2, 6. And this is 3, 0, 3. And after getting this, so what is our P inverse? P inverse is nothing but adjoint of P by determinant of P. So P, what is adjoint of P? Adjoint of P is nothing but 6. So 1 by 6 times of, this is minus 1, 2, minus 3. Minus 2, 6. And this is 3, 0, 3. And after getting this P inverse, so we have to diagonalize the matrix. For diagonalizing the matrix, see what is the formula here. Diagonal of the matrix is nothing but P inverse A into P. So first of all, we have to multiply these 3. P inverse A into P. So the diagonal matrix will be, what is a P inverse? Just now I found that this is 1 by 6 times of this is minus 1, 2, minus 3. This is minus 2, minus 2, 6, 3, 0, 3. And what is our A matrix? A is nothing but our question. So what is the question here? So A is nothing but 1 minus 1, 4. This is 1 minus 1, 4. 3, 2. 3, 2 minus 1 and 2, 1 minus 1. And next one, P. So what is the P? P is nothing but the modal matrix. So P is nothing but minus 1. See here, minus 1, minus 1, 1. This is 4, 1, 2. This is 1, 1, 1. Now I have to multiply. So if I multiply, see here, this is 1 by 6 times of this is minus 1, 2, minus 3. Minus 2, minus 2, 6. 3, 0, 3. So if I start multiplying, so this will be, see here, this is minus 1, this is minus 4, this is plus 4. So if you see, this is minus 1 and this is minus 1 again, plus 4, and this is 1, minus 2, plus 4. Plus 4. So here, so this is minus 3, plus 8. This is minus 1. So this is minus 3 plus 2 minus 1. So this is 3 plus 4 minus 1. So this is minus 2 plus 4 minus 1. So this is minus 2 plus 1 minus 1. If you see this one, this is 2 plus 2 and this is minus 2. So this is plus 4 and minus 4. Let's see any changes here. Plus 1, minus 1. See what remains? D is equal to 1 by 6 times of this is minus 1, 2, minus 3. This is minus 2, minus 2, 6, 3, 0, 3. And this value will be minus 1. And this is going to become, so this is minus 2 plus 4. This is 2 and this value is 3 and this is 8 minus 4. So this will be plus 4 and this is minus 4. This will be minus 2 and 7 minus 1. This is 6 and this is 1. This is minus 2 and this value is 3. Now if I multiply, see what happens. 1 by 6 times of, if I multiply 1 into 1, this is 1, this is 1 plus 8 and minus 3. So if I multiply minus 2, minus 4 and this is plus 6. So this is minus 3, 2 6, this is 12 and this is minus 9. So if I multiply, so this is 2, 2 4s are 8 plus 6. So this is minus 4 and this is plus 4 and minus 12. And this is minus 6, minus 12 and this is plus 18. This is minus 3 plus 0 plus 3. So this is 6 plus 0 and this is minus 6. So this is 3 3s are 9 plus 0 and again 3 3s are, this is 9. If you observe properly, this is plus 6 and minus 6. This is plus 12 and minus 12. So this is plus 8 and minus 8, plus 3 minus 3, plus 6 minus 6. And this is plus 18 minus 18. See what remains here. D is equal to 1 by 6 times of 9 minus 3. 6, 0, 0. And this is 0. So if I cancel this one, what remains? Minus 2, 0. And 0, 0. And this is plus 18. If I divide with 6 inside, then see what happens. 1, 0, 0. This is 0, minus 2, 0. And 0, 0. This is 3. And if you observe properly, what are our eigenvalues? So I'll show you the eigenvalues. So this is 1, minus 2, 3. And if you observe here, the values are 1, minus 2 and 3. So the matrix, given matrix is diagonalizable and it is diagonalized. And the eigenvalues are the elements of the diagonal of the matrix. And this is how we have to cross check. So this is very, very important, most important. And from tomorrow, I'm going to upload Cayley-Hamilton theorem problems. And very soon coming up with another video. And thank you so much for listening to me till here. And subscribe to this channel as early as possible for the latest videos. And hopefully these videos will be very helpful to you. Until then, thank you so much.